Okay, so that's the information at each one of our points, and now we want to go from point to point, right? We were looking at the path between points 1 and point 2 and 3, point 3 and 4, looking at the path and how much work is done, how much energy has to be added to the system, how much energy does the internal energy does the gas gain or lose. So let's make another table. This time we're looking at the path from 1 to 2, from 2 to 3, from 3 to 4, and from 4 back to 1. The other thing I like to do is to list a total for the cycle. And what do I care about? I care about the work done by the gas, the heat, Q, added to the system or removed from the system, and delta U, the change in internal energy of my gas. So let's start with our first path from 1 to 2. From 1 to 2, we have a process where the pressure is constant. That's one of the easiest ones because the work done is just the area under that curve. I'm going to shade it in blue here. And so it's just the pressure times delta V. We know all of that. The pressure, delta V. Remember, our deltas are always final minus initial, so that would be 1.23 times 10 to the negative 2 cubic meters multiplied by 3.07 times 10 to the minus 3. And I've got 2,215 joules positive. And it's positive because the gas is expanding, right? The gas is doing work on the environment. Positive work. Delta U. And in order to find delta U, we are going to use this equation. And the reason we can use this equation is because this is an ideal gas. This helps us out a lot. The only other thing we need now is CV. And CV can be written as R over gamma minus 1. And R we know, 8.314. And gamma we know, in this case it's 1.4. So when I plug those in, I get N 8.314, 1.4 minus 1, and I get 20.79 delta T. So now I can use this equation for delta U, and it only depends on the temperature, and I can plug in my numbers. So what I end up with now is 1/4 of a mole, 20.79, and delta T, 1,420 minus 355 Kelvin, ends up with 5,535 joules. So our gas gains some internal energy, and our Q now is delta U plus W, 5,535 plus 2215, 7,750 joules. So I can go back up and put these numbers in. The work done from 1 to 2 is positive 2215, 2,215. Delta U, 5,535 joules, and Q, 7,750 joules. Now let's go back and do the next leg from 2 to 3. This is our adiabatic process. And the definition of the adiabatic process is that Q is 0. And if Q is 0, then delta U is going to equal negative W. So we're going to first use the fact that this is an ideal gas and that delta U is N times CV times delta T, which is N times 20.79 times delta T, and I get, well, I'll just put the numbers in, 0.25, 20.79, and the T is 1875 Kelvin minus 1420 Kelvin. So I end up with a positive 2,365 joules, which means that the work done is negative 2,365 joules. Because the volume decreases, the work has to be negative. We did work on the gas in order to get it to decrease. So let me go back and plug in those numbers. The work done, negative 2,365. Delta U, positive 2,365 joules. And 0 for the heat added to the system. Now we're going from 3 to 4. This is our isothermal process. And if we have an ideal gas, the temperature doesn't change in an isothermal process. So that tells us that the delta U is going to be 0 for this process, or another way of thinking about it is Q is equal to W. And what's W for an isothermal process? We can integrate and we end up with a natural log of the final volume over the initial volume multiplied by nRT. So we can plug in some numbers here. The temperature (1420 Kelvin), and the natural log of 1/2, which is the volume 3.07 times 10 to the minus 3 divided by 6.14 times 10 to the minus 3 is 1/2. One of the volumes is twice the other one. And what does that give me? Negative 2,046 joules. So we can fill in our table one more line. Going from 3 to 4, delta U was 0. Q and W are the same, negative 2,046 joules for both of those. And we have one more step. Let's look at it. We're going from 4 back to 1. So we know one thing right off the bat, the volume does not change. So the work is 0. That means that Q equals delta U, and delta U we can solve for. And remember, it's always final temperature minus initial temperature. So T1 minus T4, and that gives us a negative 7,900 joules. Where's our table? There's our table. Delta U, negative 7,900 joules. Q, negative 7,900 joules. So let's see, 2215, negative 2365. We add those up, I've got a negative 2,196 joules. For our Q, I get the same thing. And for delta U, I get 0 because this is an ideal gas, and we start and end at the exact same condition, at the same temperature. And the internal energy of an ideal gas is only determined by temperature. So let's take a quick look here. This negative sign tells us that we did work on the gas. Right? We did work on the gas, and this negative sign tells us that we got heat out. Okay, so we did work on the gas and we got heat out, kind of like a refrigerator. We do work and the heat comes out of the refrigerator, keeps our food cold.